Example 2 for state machine design. For example 2, that you design one counting machine. Okay, let design clock synchronous state machine with two input X and Y and one output Z. Okay. There are two input X and Y and one output Z. The output Z should be 1 if the number of one input on X and Y since reset is multiple of 4 and 0 otherwise. Okay, at first you should make understand the problem. Okay, the problem and the output will be 1. Okay, I give you for some example X, Y and output Z. Okay, at the beginning if input is 0, 1, okay, when clock tick with the first set of input 0, 1, 0 for X, 1 for Y, then now the total number of logic 1 input is 1. So now output Z is 0. And if the next clock tick, if input XY is 1, 1, now total number of logic 1 input is 1, 2, 3, right? But T is not multiple of 4, so output Z still be 0. Okay, if the next input is 1, 0, okay, when clock tick, if the next input XY is 1, 0, now total number of logic 1 input is 4, right? And it's multiple of 4. So now output Z is 1. Okay, and if the input for the next clock tick is 1, 1, so now total number of logic 1 input is 1, 2, 3, 4, 5, 6. 6 is not multiple of 4. So now output Z is 0. And if the next input is 1, 1 again, now total number of logic 1 input is 8, right? So 8 is multiple of 4. That means output Z will be 1. And if the next input is, for example, 0, 0, now total number of 1 still be 8. And it's multiple of 4. So output is 1. And if the next input is 0, 1, now total number of 1 is 9. It's not multiple of 4. So output is 0. Okay, and so on. Okay, now on the property of behavior of the state machine, you should determine number of state first. Okay, how many state of this state machine? If you consider multiple of 4, okay, the condition is output will be 1 when number of input XY for logic 1 is multiple of 4, which may be 0, 4, 8, 12, and so on. Right? And because number of the number that is multiple of 4 is infinite, right? So you should define some suitable property of state that can represent all possible input. Okay, so one of these is you may think that multiple of 4, that means when you divide by 4, okay, the result will be 0, right? Okay. If input, when you count, okay, number of logic 1 input for x and y may be 0, 1, 2, 3, 4, 5, 6, 7, right? But when you divide by 4, okay, the result maybe, okay, when you do the modulo, the result may be 0, 1, 2, and 3, right, for the remainder, right? So let's define 4 state. Okay, state is 0. Okay, when you do modulo 4, okay, got the 0. Okay, namely, it's multiple of 4, right? 4 is 0. That means the output for this state is 1. And when you do modulo of 4, and the remainder, the result is 1. Namely, when you divide it by 4 and the remainder is 1, right? So it's S1, output is 0, right? And if the remainder is 2, when you divide it by 4, so it's 2, give logic 0 output. And it's 3, right? The remainder is 3 when you divide by 4 or modulo 4. This one also output is 0. Okay. First step, when you read, okay, the problem, okay, you should define, okay, state that suitable for the problem. In this case, there are 4 states and have got the meaning like this. Okay, it should cover all possible conditions. And of course, you must be able to define the output value for each state. Okay, and after that, you just, okay, consider what is the next state for all possible input. In this case, because there are 2 bits, right, 2 input, so there are 4 possibility of input combination and value. Okay, now let's consider if the current state is 0, and when Coptic input x1 is 0, 0, that means the next state should be what? It should be a0, right? Nothing changed, right? Number of logic 1 still be the same. And if the current state is s1 also, it still be s1. If the current state is s2, okay, the remainder is 2, right? So when the next input is 0, 0, so total number of logic 1 still be the same. So it still be at s2 and s3 also. But if the input is 0, 1 or 1, 0, okay, total number of logic 1 will be increased by 1. That means if the current state is S0, you go to S1 for the next state, right? If the current state is S1, the next state should be S2. If the current state is S2, when input is 0, 1, next state will be S3. And if the next state, if the current state is S3, when input is 0, 1, right? The next state should be S0, right? This one also. S1, S2, S3, and S0. And if input is 1, 1, okay, you get more 2 logic 1 input. That means when we change S0 to S2, right? S1 to S3, S2 to S0, and S3 to S1. So now you can complete the state output table. That is the first step that you should be able to do after you read the problem. Okay, and you may write state diagram, okay, from the state output table. Okay, for example, because this one, okay, I design it as more type, okay, state machine. So in state diagram, okay, I can write output inside the circle that show that this output will be 0 when it's on state S2, or this one output is 1 when the machine is on state S0, okay, for example. And if input is 0, 0, 0, 0, x prime, y prime, okay, will be the same state, okay, for 0, 0, or x prime, y prime. And if input is 0, 1 or 1, 0, okay, we go to the next step, okay, is 0 to S1, S1 to S2, S2 to S3, and S3 to S0, okay. And if input is 1, 1, okay, you skip one step, okay, this to this, this to this, and this 1 to this 1, okay, and S3 to S1, S1, when input x1 is 1, 1, okay, or when you write in transition expression, you can write it as x and y, okay, for the condition that x, y is 1, 1. Okay. Okay, now, anyway, from this example, you design by using this state output table. Okay, the next step, okay, you must change this state name, okay, to binary code or state assignment. So, from the example, I define 0, 0, 2 states S0, 0, 1, 2 S1, 1, 1, 2 S2, 1, 0, 2 S3, okay, in gray code order, okay, because from state diagram, okay, it came from this to this, this to this, this to this, this to this, right? So if I define a state assignment for each state by using gray code order, it may be reduce number of component order get, okay, when you design maybe by using K-map, okay, something like that. Okay, now after you assign, okay, binary code for each state, then now you just change, okay, the name of state to its binary code, namely 0, 0 for A0. That means every A0, okay, that you change to 0, 0, okay, and for S1 is 0, 1, okay, you change every S1 to 0, 1, okay, S2 also, okay, S2 is 1, 1, so you change S2, okay, 2 1 1. And for S3, okay, and you define it as 1 0, right? So you just replace, okay, S3 by 1 0. Okay, so now you get transition output table. After that, now for this step, you know the information about what for the basic, okay, structure. Now you know that you use two flip-flop, right? Two flip-flop for Q1 and Q2, okay? And for the design, you must decide next step logic F, output logic G, okay? And actually it's based on what type of flip-flop, okay? The easiest, okay, method that you use D flip-flop, because when clock tick, if you use D flip-flop, Q star is the same as input D, right? That means if you want Q1, for example, to be 1 when clock tick, you just apply 1 at input D. Okay? Okay. And this transition output table, okay? For the transition table, for this information is Q star. That means it shows relationship between the output Q when clock tick or Q star relate with input of F. Input of F is X, Y, and feedback from Q1, Q2. To decide this F, to decide this circuit F, you must know relationship between output of F and input of F, right? Output of F is excitation signal. That will be what? That will be D1 and D2. So if you use D flip-flop, you can write the excitation table. Will show you the value of D1 star and D2 star easily, because don't star, just D1 and D2. Okay, D1 will be same as Q1 star, and D2 same value of Q2 star. So you can copy this transition table to excitation table. After that, if you know information about this output of F and input of F, so you can design this circuit F as the normal combinational circuit. Okay, so for this sample, let's use D flip-flop. That means if you want D1, okay, if you want Q1 star to be 0, you must apply input of flip-flop D1 to 0 also. And if you want Q2 star to be 0, so you must apply 0 to D2, right? Same value. So you can copy this to this. So now you know the information, okay, of excitation signal. Okay. So from this one, you can maybe using Kmap to design circuit F by determine the excitation equation by using Kmap for D1 and D2. Okay, for D1 is this bit, right? This bit 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0. You just copy this one and write down in Kmap, right? And just be careful about the order, okay, of input xy and state variable. In Kmap, you must write in the order of gray code. But sometimes state excitation table, the order of input or state variable is maybe not gray code. Okay? Sometimes it's binary code, something like that. So you should be careful to write down from excitation applicable to Kmap. Okay, when you write Kmap, the next step you just find out equation from this Kmap by select. Okay, you want to minimize, right? You may select this one, and the product term is x prime, y prime, and q1, for example. And okay, select this term. You must select all of logic one, right? Maybe select this one. This one is x prime, y, and q2. And this one is what? X, y, and q1 prime. And this term is what? X and y prime and q2. So get equation, okay, for d1. For d2 also, okay, you just write, okay, the value of d2 from excitation table to Kmap for d2. And after that, you just use this Kmap to find our equation for d2. For example, okay, this one, it's x and y and q2 prime, right? And for this one, x and y prime and q1 prime, and this term is x prime, y prime, and q2, and this term is x prime, y, and q1 prime, okay, something like this. Okay, so you can find the equation for d1, d2, and from this excitation equation, so now you can, okay, draw the circuit diagram for next state logic F. And now you use two flip-flop, right? Flip-flop and Q, and use common clock. And the last one, you must write down the circuit diagram for G. So you must show output equation. So it's very easy, okay? From excitation table, this column and this column, or you may use from transition table also. Okay. So from this one, the output Z is 1 when input Q1, Q2 is 0, 0, right? That means output Z is Q1 prime and Q2 prime. Okay, that's all. So you can draw the circuit diagram for output logic G. Okay. So now you can complete the state machine for this example. Okay. Next, example 3. When you design a combination lock. Okay, let you design a clock synchronous state machine with one input X and two output, unlock and hint. The unlock output should be 1 if and only if X is 0 and the sequence of inputs received on X at the preceding 7 clock tick was 0, 1, 1, 0, 1, 1, 1. The output hint should be 1 if and only if the current value of X is the correct one to move to the machine closer to being in the unlock state, which unlock is 1. For this problem, there are two output, unlock and hint, and there's one input X. Okay, let's consider unlock output first. For unlock output, unlock will be 1. Unlock will be 1 when the sequence of input X for the preceding 7 clock tick was 0, 1, 1, 0, 1, 1, 1. Okay, the one is something like password, right? And when you keep password for first of all in computer, after you keep password, and then you press maybe sometimes enter key, right? But in this case, because there's only one input, so that you use, okay, the value of X is 0, okay, as you press enter key in the computer, something like that. That means if you apply input of 0, 1, 1, 0, 1, 1, 1, and when you apply 0, okay, then the output will output unlock will be 1 suddenly. Okay, so from this, if you consider for unlock first, that mean the output unlock will be 1 when you the machine, okay, get this 0, 1, 1, 0, 1, 1, 1, right? It as the password correctly, and when input X is 0, output unlock will be 1. So from by this condition, this state machine should have 1, 2, 1, 2, 3, 4, 5, 6, 7, and no any bit is correct for the password. That means it should have 8 states. In this case, the default state A is got 0, okay? No any bit collect. Okay. And state B collect 1 bit. State C correct 2 bit. State D correct 3 bit. 0, 1, 1. Okay, from this 0, 1, 1. State E, okay, 4 bit correct 0110. State F 5-bit correct. State G 6-bit correct. And state H 7-bit correct. At state H, when input X is 0, output unlock will be 1. Okay, based on this condition. And for another state, output unlock is 0. 0, 0, 0. Okay, 0, 0, 0, 0, 0. And 0 at this state H. Okay, when X is 1, output unlock is 0. And what about hint? Hint, okay, as name is for hint. For example, at state A, if the user apply value X is 0, so is right, correct, right? Password, right? For the first digit. So when you apply 0 or apply X at state A, hint will be 1. But if you apply 1, hint will be 0. Okay, and at state B, state B already get 1 bit correct of 0, right? If you apply the next value of X is 1, so hint will be 1. But if not, if you apply 0, hint will be 0. Okay. And so on. So for the hint, it's something like this. Okay. Now for state C 01, if you apply next value of X is 1, so hint will be 1. If not, X will be 0. Okay, and so on. Okay, so now you can define output for each state for all possible value of input X. And to complete this state output table, you must find out the next state for each state. Okay, at state A, if when clock tick, if X is 0, correct, 1 digit, right? So it should go to state B. But if input is 1, it still be state A, right? Okay. And at state B, if the next input is 1, it is correct, go to state C. But if the input is 0, okay, 0, what is the next step? If you use maybe actually there are two ways to do. First one, if you apply some incorrect digit or incorrect password, let it reset and start at the beginning again. Or you can reuse the password. For example, if you at state B, right? When you apply 0, at state B you get 0, right? And the next input is 0. So it's not correct, right? Okay, it's not correct. When it's not correct, okay. But this 0 may be the first digit, okay, for the correct sequence of the password. So you can define the next state of this state B to B, because this 0, it is possible to be one of the correct password. Okay, you can reduce this digit. Okay, and at state C, if the next input is 1, at state C you already get 2-bit correct, right, of 0 1. And if the input is 1, it go to state D. But if not, if the input is 0, and you can reduce this 0, right, as the first digit for the correct password. So this is B. Okay. After that, for state D, if the input is 0, it's go to E, right? Go to E. But if the input is 1, it cannot back to C or B. Okay, it should back to A, right? Okay, back to A. And at state E already get 4-bit correctly. If the next input is 0, it's not correct, right? For 0 is okay, it can back to state B to reduce this 0. And if next input is 1, go to F. Okay. At state F, if the next input is 1, it go to G. If the input is 0, it's go to what? Okay, go to B, right? Okay, and at state G, for state G already correct 6 bits, right? If the next input is 1, go to H. But if the next input is 0, okay, it's not correct. It's not correct, but you can reduce this 4-bit, right? 0 1 0 0 0 1 1 0, sorry, 0 1 1 0. Okay, it can be state E, right? That means if you apply 0 and you apply what, 1 1 1 for the next, it can be correct password. So you can reduce this 4-bit 0 1 1 0. So go to state E. Okay, and at state H, at state H, if you apply 0, go to B. If you apply 1, just go to A. That's all. Okay, when you complete this step output table, the next step you must do what? Yes, state assignment. To assign binary code for this 8 state. So because at 8 state you may use 3-bit, right, of binary code to represent this 3 state. So in this case I use binary counting order for state A to H. So from this one, A is 0 0 0, B is 0 0 1, C is 0 1 0 until 1 1 1. So for in this you can replace A by 0 0 and replace B with 0 0 1, right? 0 0 1 0 0 1. Okay. So you can get this transition table, transition output table. And if you use D flip-flop for the design, the excitation table, okay, excitation signal of D1, D2, D3, okay, the same as Q1 star, Q2 star, Q3 star. So it's the same value in the table. Okay, after that Okay, you can use Kmap, okay, to find out the circuit for next state logic F and output logic G. Okay, in this example, you use 3 flip-flop, and if you use D flip-flop, it's very easy, right? And output Q, you use Q1, Q2, Q3. So input or excitation signal is D1, D2, D3. So from this one, if you want to find out equation for D1, so you just consider this bit, right? It is correct. It's value of D1. So from this one, you can write Kmap for D1, D2, D3 also. And for output equation, unlock and hint, you just consider this bit and this bit, okay, respectively. So just write down Kmap for each excitation signal and output signal, and then you just select, right, logic 1 cell in the Kmap. So after that you will get our equation for design the state machine. So that's all for this example. And for more example, let me write down it here. Okay, if I want to design 2-bit binary counter, I can count up and count down, get this circuit. If there's one input X, one input X to control 2-bit output Y1, Y0. And let Y1, Y0 is maybe 0, 0, okay, 0, 1, 1, 0, and 1, 1, right? If input X is 0, if X is 0, let count up, namely the state will change in this order: 0, 0, when clock tick, change to 0, 1, when clock tick, change to 1, 0, when clock tick, change to 1, 1, and when clock tick, back to 0, 0. This is when X is 0, or X prime, X prime, X prime, X prime. But when X is 1, let's count down. Okay, count down 1, 1, 2, 1, 0, 1, 0, 2, 0, 1, 0, 1, 2, 0, 0, and 2, 1, 1. So when count down this direction, okay, this direction, X, right? X, 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 okay? Or if you write state output table, you can write something like this. Okay, let I define this state S0, S1, S2, and S3. Okay, so I can write something like this: S0, S1, S2, S3, and input X when input X is 0 and input X is 1. write table, something like this. Okay, this is next step, and output y1 y0 y1 y0. Okay, let write output first. 0 for is0, 01 for is1, 10 for state is2, and 11 for state is3. And how about the next step? When counting, when x is 0 is count out, right? Count up, that means check is0 to is1, is1 to is2, is2 to is3, is3 to is0. And for input 1 is count down. That means S3 to S2, S2 to S1, S1 to S0, S0 to S3. Okay, this is state output table. And then when you use state assignment, okay, after you get this one, get the next step, you just write down, okay, because there are 1, 2, 3, 4 states. So you may use 2-bit of state variable, okay, Q1, Q0. Okay, to make it easy, let identify okay state assignment for 0 for is0, 014 is 1, and 104 is 2, 114 is 3. Okay, so use binary counting order. The value of output y1 y0, okay, will be the same as q1 q0. The mean equation, output equation for y1 and y0 is very easy. Namely, y1 is same as q1, right? And y0 is q0. Okay, this output equation. Okay, you can get it suddenly after you do state assignment. And what about the next state? When input x is 0, the value of q1 star, q0 star is what? Okay, from this one, right? And the next state of S0 when input x is 0 is S1. S1 you define it as 10, right? So you write, 01. So you write 01 at here. Okay. For S2 is 10, S3 is 11, S0 is 00. Okay, you just replace, okay, state name by binary code. So S3 is 11, 00, 01, and 10. Okay. Now you get state output table, okay, to show the relationship between output of flip-flop when counted and what? To flip-flop, right? Output Q1, Q0. Output of flip-flop or state variable. And input of circuit F. In this case, there is one external input and feedback from flip-flop Q1, Q0. Okay, this is shown by this Q1, Q0 star, and input of F, X, and Q1, Q0. Okay, by this column and this one, show output equation for output logic G. This one. Y1, Y0. In this case, it's very easy, right? No any logic gate need. Okay, you just connect directly. Okay, from Q1 to Y1 and Q0 to Y0. Okay, now let you find out circuit diagram for next state logic F. Okay, the problem is what kind of flip-flop that you want to use as state memory. Okay, for state memory, you may use D flip-flop, JK flip-flop, or T flip-flop with enable, something like that. Okay, first one I will show you if you use D flip-flop. Okay, let's try D flip-flop. So if you use D flip-flop, okay, you must write down excitation table, right, for D flip-flop. For D flip-flop, because D flip-flop, okay, when clock tick, Q will read data from D, right? Then Q star will be the same as D. So from this table, actually, you can copy. Okay, copy this table. Okay, and change the name. Change this one to be what? D1 and D0. So now you get an excitation table that can find excitation equation for circuit F, namely for D1. Okay, so you can consider from this directly, or you can write down a K-map for D1 and K-map for D0. Okay, let write K-map for D1 and D0 to find excitation equation. So take this Q1, Q0, and input X 01, and just be careful for the order. Okay, in this table, you use binary, right? Binary counting, but in K-map you must use record, right? Record 01, 11, and 10. So for D1 is 0110, right? Change color 0110, 0110. Okay, it swap from this 10 and 11 here, so you must swap from this also. And for this bit is 1001, 1001. This is for D1. Similarly for D2. For D2 also, you can do the same thing. Q1, Q0, 00, 01, 1110, and input X 01. For D0, 1, this bit, right? 1010, 10, 1010, 1010, 1010. It is D0. Okay. So after that, you just select, okay, all logic 1 from this one, this cell, this cell, this cell, this cell, right? And this is maybe get XOR, right, between Q1, Q0 and X. Q1 XOR Q0 XOR X, right? Because it's 1 when the number of logic 1 value of Q1, Q0 and X is odd, right? To give logic 1 result. So it's XOR between these three variables. And for D0, when you select this and this group together, so it's what? Q0 prime. Q0 prime. So by using this excitation table of D1 and D0, you can write a circuit diagram for next state logic F. Namely, choose XOR, right? XOR gate. If I write by using two input XOR gate, you can write the circuit diagram like this. This is for D1. D1 is Q1. Okay. And this is Q0. D0. The same clock. Use this clock. Okay, common clock. This clock. And D0 is Q0 prime. Q0 prime. That means in your flip-flop have got negative output or active flow output of Q0. You can use this one, okay? Connect directly to D0. Okay. And for D1, XOR between Q1, Q0, and X. This connect to external input X. This is maybe from Q1 and Q0. Okay, so and this output is circuit G. Okay. Nothing in circuit G, right? Circuit G. Nothing. You can connect directly to Y1 and Y0. Okay, that's all for this by using the flip-flop. Okay. How about if I use not the flip-flop but use, for example, JK flip-flop. So use JK flip-flop. JK flip-flop. Okay. From this transition table, I must generate excitation table, right? For input X is 0 and 1, and you have two flip-flop, right? So it should have J1, K1, and J2, K2. It is Q1, Q0, 0, 0, 1, 1, 0, and 1, 1. And output Y1, Y0. Okay, output is the same. 0, 0, 1, 1 0 and 1 1. For JK flip-flop, if you want to change Q to Q star, right? Maybe what? 0 2 0, 0 2 1, 1 2 0, and 1 2 1, right? Okay, if you want 0 2 0, and you must apply JK as 0 0. Okay, if you consider it as hold mode. But if you consider it reset, that means K must be 1, J is 0. So you apply 0, don't care. And for 0 1, we treat as toggle or set 1 0. Okay, 1 don't care. And 1 0 is toggle or reset, right? Case 1, J is 0, don't care 1. And 1 1, 1 1, and maybe hold 0 0 or set J is 1, K is 0, or don't care 0. So from this application table, this one, okay, you can fill the value of JK for this condition. Okay, if the transition transform Q to Q star like this, we apply value of JK like this. For example, for Q1, say 0 to 0. If you want Q1 change from 0 to 0 for Q1 star, that means you must apply 0 don't care for J1, K1, right? So apply 0 don't care here. Okay. Okay. So let's complete this table. 0 don't care for J1, K1. 0 to 1, 0 to 1, 1 don't care. 1 to 1, 1 to 1 don't care 0. 1 to 0, 1 to 0 don't care 1. For input x is 0. And for input x is 1, Q1 change 0 to 1, 0 to 1, 1 don't care. 1 don't care. 0 to 0 don't and 0 don't care. And Q1 change 1 to 0, 1 to 0 don't care 1. And Q1 change from 1 to 1 don't care 0. Okay, this is for J1, K1. Okay, when input x is 1. And for J, I'm sorry, it should be J0, K0. Okay, sorry. It should be J0, K0 because I use Q0. Okay, for J0, K0, let's consider this bit, right? To this one. 0 to 1, 0 to 1, 1 don't care. 1 don't care. 1 to 0, 1 to 0 don't care 1. Don't care 1. And 0 to 1, 0 to 1, 1 don't care. And 1 to 0, 1 to 0 don't care 1. When input x is 1, change 0 to 1, 0 to 1, 1 don't care. 1 to 0, 1 to 0, don't care 1. And what else? 0 to 1, 0 to 1, 1, don't care. And the last one, 1 to 0, 1 to 0, don't care 1. This is for J0, K0. Okay. And after that, you just draw K-map. Okay. For J1, for K1, for J0, and for K0. Okay. 4 set of K-map. Okay. So, okay, let's write K-map for J1 first. So maybe I can write something like this. Value of Q1, Q0, and X 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. I copy this. But I need to use 4 set of K-map. This one, and this one. Okay. For J1 first. J1 is 0, 1, don't care. 0, 1, don't care. Be careful about the order of binary order and gray code. And when X is 1, J1 is 1, 0, don't care. 1, 0, don't care. Right? And for K1 is don't care, 0, 1. Don't care, 0, 1. And don't care, 1, 0. Don't care, 1, 0. And for J0 is 1, don't care, 1, don't care. 1, don't care, 1, don't care. And 1, don't care, 1, don't care. 1, don't care, 1, don't care. And for K0 is don't care, 1, don't care, 1. 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 Okay, something like this. Okay, this is for what? For J1, K1, J0, and K0. For K0 is quite easy, right? You select all of this. Okay, K is 1. J0 also. Okay, select all. J0 is 1. How about K1? For K1, you can select this. Okay, this is X prime and Q0. And for this product term is X Q0 prime or X or Q0. What about J1? For J1, if you select this term, it's X prime Q0. And for this one, it is what? It's X Q 0 prime, or x XOR Q0, or same as K. That means to implement the circuit, use JK flip-flop, right? To JK flip-flop, J1, K1, Q1, and J0, K0, Q0 is common clock. Is clock. Okay, clock. And output connect directly to okay, Y1 connect directly to Q1, Y0 connect directly to Q0. Okay, as the previous example when you use D flip-flop. The difference is now you use JK flip-flop. Okay, the circuit F is different. K1, J1 is X XOR Q0. So you use XOR gate, right? XOR gate. Now, and XOR X and Q0. This is Q0. And for K0, K0 is 1. So you connect to logic 1 directly at here. Okay, that's all for circuit when you use JK flip-flop as state memory. And okay, what about if I use T flip-flop with enable? Flip-flop with enable. Okay, this one. Enable clock. Enable clock. Maybe Q1 at here and Q0 at here. So this is enable 0 and enable, enable 1 and enable 0 as here. Okay, for the output is the same as the previous example, Y1 at here, Y0 at here. So let you design circuit F. Okay, this circuit F. Okay, again from this transition table, from this, okay, let you write down excitation table when you use T flip-flop with enable. Q1, Q0, X is 0, X is 1, output is the same, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay, now excitation is enable 1 and enable 0. For T flip-flop is easy, right? Namely, if you want to change 0 to 0, it's not toggle, right? Enable is 0. And 0 to 1 is change, right? Enable is 1. 1 to 1, not change. Enable is 0. 1 to 0. Okay, not change. No, sorry, it's change, right? 1 to 0 is toggle. So enable is 1. And 0, when input X is 1, 0 to 1 is toggle. 0 to 0, not toggle. 1 to 0, toggle. 1 to 1, hold. Okay. And for Q0, okay, for Q0, change to Q0 star. Enable 0 should be what? 0 to 1, toggle. 0, 1 to 0, toggle. 0 to 1 toggle, 1 to 0 toggle, and when input X is 1, 0 to 1, 1 to 0, 0 to 1, 1 to 0, toggle, 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 toggle. So, okay, from this is be easy, right? So, if you write keymap, okay, let's write keymap for enable 1, the Q1, Q0, X 0, 0, 0, 1, 1, 1, 1, 0, X 0, 1. Enable 1 is 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0. And for this enable 1, for enable 0, all is 1, right? So actually you can write suddenly is 1. Okay, if you like keymap, you can complete it with 1. Okay. So for enable 1, if I select this, so I change color to this. So it's X prime and Q0. And for this product term is X and Q0 prime, or X XOR Q0. So based on this excitation equation, enable 0 is 1. So connect this is 2 logic 1, and enable 1 is XOR between X and Q0. This Q0 XOR X. Okay, that's all. We use T flip-flop with enable. Okay, show you okay to design by using different type of flip-flop. Okay, get to connect these two clock. Okay, this is example. Okay. When you use different type of flip-flop to the design. No, the circuit is different, right? For circuit F. Okay, next state logic. And this is when you use JK flip-flop. And this is when you use D flip-flop as state memory. Okay, that's all for today.